definition for piecewise smooth certain maps, please.
Thank you for the invitation and thank you for coming. It's a great pleasure to be here. So first, of course, I need to say that what I'm going to talk about is relatively recently submitted article joined with Frank Trujillo. And okay, so let me first maybe state what I'm going to talk about. So I need to somehow the title is a little bit misleading because it's wrong, but we couldn't find a better one. So I will explain in a moment what I mean by that. But first, so we have circle maps. So circle maps, the most standard classical maps are the homeos and diffeos of a circle, and this is where we start the history with. So before I'm able to formulate our main results, I need to first say what is the setup, what is the actual objects that we want to study. So first of all, what is the goal? So the goal is to study rigidity, but already the word rigidity has many meanings, right? Study the rigidity of isomorphisms, between two. I only will write this name once in its whole, so it's generalized interval exchange transformations.
Between two, TWO.
What?
Between two.
Between. Thank you. Between two generalized interval exchange transformations. Which are satisfy proper technical conditions, whatever that means. You can think about smoothness conditions, about some properties of the locally defined derivative, proper technical conditions. Okay. So those objects, generalized interval exchange transformations, don't worry, I will write what I mean by that very, very soon. But they appear as generalizations actually of circle diffeos. So first, let me introduce some very, very already classical history. So let me write over here. It's a history. So it started already with Poincaré. Okay, so he proved that if F is a it's a diffeomorphism, it's a C1 diffeo of a circle, then it is topologically conjugated to rotation R, say rho, by rho, where rho is a rotation number of F, and I already made a mistake because here I should put semi-conjugated to rotation by rho. Sorry, this is actually very important. So we have a semi-conjugation. So what do I mean by semi-conjugation? It means there exists a continuous map of a circle, continuous. Right, so the continuous corresponds to the word topologically, such that if I first act by S and then act by a rotation by rho, this is the same as first acting by map F and then acting by S. So this is one direction. If S was invertible, then we would actually have a conjugacy, but it doesn't necessarily have to be true. Okay, and for many years people were trying to improve the results, and there are many classical results, like what can be said. So perhaps the most important that I need to mention here is the result by Danjoua. Danjoua proved that if F is C2, then it is conjugated to R rho. I didn't say something. I will always assume that I preserve the orientation. We don't consider orientation reversing maps over here. Okay, and then, so what you can see from that in particular, so here again, sorry, I'm losing the most important words I don't write. I mean topologically conjugate, right? So what you can see even from that result that in general we will expect some drop of the regularity. So we have so our function f is topologically isomorphic to rho, but we cannot say anything more. So we assume C2. We don't assume any kind of smoothness. I mean, we don't get any kind of smoothness on the conjugacy itself, and in general, we cannot. But then we have the results. What happens if we actually improve? I mean, we not improve. We actually assume something more about F. So this is result by Hermanio-Cos. So this is already, I think, late 70s or 80s even, proved. So that if F is C infinity, then the conjugacy, so first of all, the conjugacy exists via Danjoua, but it's also in C infinity. It's also C infinity, but if rho, the rotation number, satisfies some suitable Diophantine conditions. Satisfies some full measure, but still Diophantine conditions. Okay, so this is already, we can see that we have a new player. So the rotation number plays the role also in this kind of results, right? So to summarize, so we have say to diffeo, and okay, we know that it is semi-conjugated to a rotation. So first of all, we can ask when it is conjugated, and okay, if we have this conjugacy, what can we say about it, right? What is the smoothness, what is the regularity? So we see that, okay, Danjoua already proved that we have, if we assume C2, we have topological conjugacy, and Hermanio-Cos proved that, okay, if we go all the way to the end, and you actually, so this is my infinity, sorry. So this is C infinity, then we also get C infinity. So
Hermanio-Cos theory says more. CR and says how much smoothness is lost.
Yes, so it's always 2, but we can also get some Helder coefficient even
but
from the
higher CR, then in the conjugacy you lose 2 plus maybe epsilon plus something related with rho.
Exactly.
I don't remember the formula.
Sorry, I also don't remember exactly, but it's true that they really describe the.
So it's very precise.
Yes, thank you for this comment. Yes, but true, but I don't remember it, so I don't want to lie, but it's true that they give a precise description. So, okay, but this is not what so this is not exactly what we are interested in. So we are interested in something else. So we are, here you can see, okay, forget about generalized interpolation transformation and focus on the word two. So we are actually trying to consider, we don't want to compare f with the rotation by its rotation number. We'd rather ask in a different question. What if you have two diffeos with the same rotation number? Then what can you say about the regularity of the conjugacy, but between them, not between the rotation? So you can see, for example, from the result of Donjoua that if you take two f and g's with the same rotation number, then they are naturally topologically conjugate to each other because you just take the compositions of the appropriate conjugacies. Yes. Okay. So this is what we want to. So okay. So in the case of circle diffeos, this is exactly done like that. So we just conjugate everything to a rotation, and then we compose the conjugacies. But what if we want to choose a more what if we want to consider a more general class of maps? So what if f is not that smooth? So we can break smoothness, okay, a little bit. So we can break smoothness in two ways. So the question, what if f is not smooth everywhere? Okay, so probably for me smooth means many things. So it depends what is the regime. So it can be the C2, C3, C infinity. So this, so you can, if you don't like the word smooth, you can replace with regular. Okay. So and two cases were considered. Two cases were considered. So two cases were considered. So first of all, we can consider circle diffeos with critical points. Critical points meaning the derivative vanishes somewhere.
So it is homeo, but differ except these critical points.
Exactly.
No,
so
no, not at this point.
that's so yes. So basically, the inverse of this transformation not necessarily have to be differentiable at this point. So this is one case, and the other case.
Finitely many?
Always finitely many.
Can you read what you wrote? Could you please read after the star?
Circle diffeos with critical points. And now I'm adding finitely many. Okay, and the case which will be which we will consider. So the case now is that the different it's simply not differentiable, meaning that we have finitely many points. Okay, now I will write finitely many points. Many points with the left. So we assume that the left hand side and right hand side derivative exists, but they are not equal.
So it's piecewise diffeomorphism.
It's a piecewise diffeomorphism.
Including behavior on the boundaries.
Yes.
Okay.
So it's exactly. So it's a piecewise diffeomorphism. So in the case under some assumptions first case, your course showed that conjugacy persists, meaning that if we add finitely many points, but still it's a nice C2 diffeomorphism, we are still conjugate to the rotation. And in the second case, this was also shown, but this time by Erman. It is also true. It is also true. And was done by Erman. Okay, and we now, what we focus in our work is exactly the second case.
In the second case, do you allow at these non-differentiability points that difference between so can be zero? That's my question. Can differential left or right be zero, or you assume they are both non-zero?
So we will assume that they are both non-zero.
Okay.
So we will assume they're both non-zero. Thank you for this question, because actually, when only one of them is zero, as far as I know, like almost nothing is known. So there is like a lot to do there, and I know that the some communities are working to try harder what is happening over there. Okay, so in the second, so we have a conjugacy, topological conjugacy, all right? So we have so assume that we have then that conjugate. So we have conjugacy to a rotation. So assume again we have a piecewise differentiable map, which is topologically conjugate to a rotation. And notice that, I mean, from a very simple reason, we cannot improve topological conjugacy to any kind of smooth conjugacy, because rotation itself is a diffeomorphism. So we would have the composition of diffeomorphisms would give me a non-diffeomorphic transformation, which is of course absorbed. But still, the question remains valid. So let me write this down maybe. So I will use this. So for regularity reasons, topological conjugacy cannot be improved Okay, but the question remains, what if F and the G are piecewise diffuse of a circle with the same kind, whatever that means, I will explain in a moment, of singularities. And by the same kind of singularities, in case of piecewise circle diffuse, I simply mean that first of all, the conjugacy, which we know it exists, assuming of course some regularity, I'm sorry, here let's assume this is piecewise diffuse, but actually let's assume at least C2. So first of all, this conjugacy which exists, so first it has to send this continuity, those breakpoints into breakpoints. By breakpoints, I mean the points where this is happening. And second of all, it needs to preserve the nature of those points, basically meaning that the ratio between the left-hand side and the right-hand side of the derivative is of the left-hand side and right-hand side derivative is exactly the same. Okay, so this is actually, this is called a break. So this is a break. So singularities. So that is the conjugacy given by your cause, by Hermann, sends breakpoints into breakpoints and does not change the ratio of the derivative, part of the one-sided derivatives. So if I consider two such transformations, I still can hope to have a smooth conjugacy. And this is what we are going to, and this is going to be the main subject of our results. But first, so in the case of a single break, so assume that you have only one point where it happens. This is a well-known result by Kanin and Teplinsky, which I am now going to cite. So, in case
Kanin and who?
Teplinsky.
From Ukraine?
Yes.
I know. Kanin is Kostya Kanin.
Kostya Kanin, yes.
Many results now. And with scenarios.
I'm actually going in a moment to mention
Okay,
another
okay.
result of his.
About the first case, you would not consider, I think there's a big literature when the derivative is zero, and Jacek Graczyk and Greg Świątek were also working.
Yes.
Okay, but this is the first case, you consider the second case.
Yes. Thank you. So in case of one break, we have the following. Theorem. So we have theorem, and this is, like I said, so it's Kanin Teplinsky. I'm sorry, I'm polonizing his last name, I know that. So let F and G be C2 plus alpha smooth orientation preserving circle diffuse with one breakpoint. One breakpoint. So it's going to be, say, we can always assume by rotating that this point is 0. So with one breakpoint at 0, or 1, depending on what's the model of the circle that you like the most, and such that the derivative at 0, the ratio of the derivatives for one function, for one diffeo is the same as for the other. And they have the same rotation number. Otherwise, there is no chance for them to be.
I have a question. I understand that all the time you assume that the rotation number is irrational. Yes?
Thank you for this comment. Yes, everywhere I assume all of those that the rotation number is irrational. Exactly. Thank you. This is a very important fact. Yes. Then such that and have the same rotation number rho, and rho satisfies some Diophantine conditions which are of full measure. Then they are 1C1 conjugate. And right away, so of course the natural question is whether we can take any irrational number, but then we have also Kanin, but this time with, I think, yes, Kanin, no, sorry, Kocic-Teplinsky. So, can I write here? Or no, because maybe people...
Yes, yes.
Okay.
Yes, if you can imagine.
Oh, that's amazing. So remark, Kocic, or Teplinsky, and Teplinsky shows that the above result does not hold for every irrational rotation number. So once again, the rotation number plays the role. Okay, so
I have a question. So what is the condition, Diophantine condition? Is it Bruno type or something?
it's something less. So it means basically that so it's a condition on the partial denominators, and it tells you that basically the difference between, if I remember correctly, that the difference between alpha and Pn over Qn, where Pn and Qn is the partial quotient, is less than 1 over some constant over 1 plus over 1, sorry, some constant over Qn to the power 1 plus alpha asymptotically, where alpha is any number bigger than 0.
Precisely Diophantine condition, not something.
Yes.
Yeah.
And this conjugation is smooth also at this breakpoint?
Yes, so that's the whole point. So that's the whole, yes. So the conjugacy is also smooth in this breakpoint. So those conditions were required for this to happen. Okay. So now I can pass. So this is what is known for the circles. So at least, okay, there's no more, but these are the results that I wanted to mention. So now I will pass to the case of what happens if we have more than one break. Okay, so this is a natural generalization.
You assume continuity at the breakpoints, right?
Always.
Always, because you promised something about interval exchange transformation.
Then I will not assume continuity at
That's
break.
why I ask.
Mhm.
Now you are not in the world of
No, because
interaction, but special. That's
we
what
are
I
still
said.
in the world of circle homeos in particular.
Okay.
Oh, I will erase one color, and I can continue. And so now what happens? In more breaks? So what happens? So question: what happens? Oops. I think I'm going to exhaust all the chalk of Impan. Okay. Happens when we have more breaks. And here I will say we don't know much. We do not know much. Well, now we know more. But okay. So first I need to introduce some notation. So I will call jump ratio. So definition. So we have a jump ratio. It's exactly what I wrote over there. So it's going to be f of x is equal df, so I think, or it's actually the opposite of what I wrote. So it's the ratio between the derivatives, and then the breakpoints are going to be bp of f is going to be the set of those points in the circle, such that, as you can imagine, sigma f of x is not 1. Okay? And then we have a theorem from 2014. This is the theorem by Cunha and Dias-Manya. Kleiber, Cunha, Dias-Manya in 2014. So let f and g be two break equivalent I will say in a moment what does it mean, but you can already imagine it simply means that breaks are sent into breaks, and the ratio of the image and pre-image, the jump ratio is the same. So the two break equivalent C2 plus and some holder diffuse with breaks. That is, there exists H, a homeomorphism homeo of a circle, such that H composed with F is equal G composed with H, and the set of breakpoints is sent into set of breakpoints, and sigma f, and as now I write what I said, so sigma f of x is equal exactly sigma g of h of x for all x in Vp f. Okay, so once again, so these are the assumptions. So we are taking two C2 plus ni diffuse with breaks, which are break equivalent. What does it mean? It means that the homeo, which we know that exists, so this was proved from this result by Erman, so such that first of all it sends the breakpoints into breakpoints, and then we also have that the jump ratios in the image and pre-image are exactly the same. Okay?
Is it theorem or assumption? This is theorem. What is?
No, this is an assumption. Sorry, this is an assumption. This is basically what I mean by break equivalent.
Okay. Ah, okay.
Okay. And if, and now this is, I'm going to use a new type of notion. So if, and I will use for the first time GIETs. So if they are of bounded type but as GIETs, then they are C1 conjugate. And now, of course, is the something that haven't appeared before. So what does it mean, bounded type? Well, for bounded type rotation, it's, I think it's well known. It means that the sequence of partial quotients in the chain fraction expansion is bounded. It's uniformly bounded, right? So this is what it means for rotations to be of bounded type. But here we have something more, because we have bounded type as GIETs. So what does it mean? Well, for that I have to finally define what GIETs Okay? So let me erase this. And let me draw a picture. So let me draw a picture of something which is of the piecewise diffuse that we consider. So we can, of course, we can identify the circle with an interval, right? And we can divide. We will divide our interval into pieces. And then the map that is piecewise diffuse is the following. So we have like something like this, something like this, something like this. Then we have like that, and I don't know how much it is visible, probably not much, but I was trying the left-hand side and right-hand side derivative at those points to be different. No, it's actually here we can or we do not, but we don't have to have a discontinuity point. Sorry, break point. So this is how the piecewise diffuse of a circle looks like. So what we can see is that what does it mean to be piecewise circle diffuse? It means that you have some partitioning to intervals, such that restricted to each of those intervals, you are actually a diffeomorphism. And this is exactly what is the definition of a GIET. So a generalized, so the definition. A GIET, here I will use, let me just see what notation I want to use. Still F, okay. F of an interval is a bijection, sorry, a GF on the interval into itself is a bijection of 0, 1 such that there exists a partition with finite partition sorry, maybe I equal 0, 1, where I is from 1 to D, such that F restricted to each of the i's is a diffeo onto with its onto its image.
Does it need to be orientation preserving? Does it need to be orientation preserving?
It is, we always, sorry, so we always assume that everything is at least, so in this case we will assume that it's partially orientation preserving. So in general, so this class is much wider than what I drew over here. So in this case we have something which I will refer to as a generalized interval exchange transformation of a rotation type, which is basically that it looks like a rotation which was perturbed, right? So it's exactly, so the intervals are switched somehow on my interval, but they still are switched just as they are switched for the rotation.
Do you still assume continuity except one?
So that's thank you. So here we do not assume. So
okay.
In general,
that's why you call it interval exchange.
Transformation, exactly. But so if I have a generalized interval exchange of a rotation type, then I do have continuity.
Okay.
If I just take this definition, then I absolutely don't have to have don't have to.
Do we assume the good behavior of the derivative at the endpoints?
So yes, we assume that the
both,
left and the right
endpoints. At both endpoints.
At both endpoints. So yes, we in general assume that the derivative exists and it's non-zero. And now, okay, so So now we are getting into the world of the interval exchange transformations. So there are two very important subfamilies of generalized interval.
Here it was bounded type as you did.
Yes, I need to, yes.
You will define.
Yes, that's actually what I'm heading to. I need to say what it means bounded type in this case. But to say what does it mean to be bounded type in this case, I have to pass to something. So GIETs are, in some sense, generalizations of piecewise simple diffeomorphism with breakpoints, for me at least. Then I have to pass to the natural generalization of a rotation, which is an interval exchange transformation, because all the notations comes from there. But because so, if I will use the same notation. If FIE is just a translation for every from 1 to D, then F is an interval exchange transformation. So this is IT. If there is not the only class that will be interested for me, because IT are somehow like rotations in the sense that if I will now assume that some ratios are not proper, some ratios of the derivatives, I will also not be comparing my map to an interval exchange. I will so not to interval exchange, but to something more general than interval exchange, something that sees different. It's still very regular, but sees different ratio of derivatives, and these are called affine interval exchange transformations. So if F composed with II is an affine transformation, then F, as you can imagine, is an affine interval exchange transformation. So these are only definitions, but those definitions are going to be used in a moment. So now I am finally ready to introduce to you the algorithm which serves as a definition for the rotation number, but in case when we have interval exchange transformation, not a rotation. Okay? And then I will be able to tell you what does it mean bounded type. With the simplest possible case. So the simplest possible case is when I'm considering interval exchange transformations. They are very nice because they are just, you can see them as ITs. So you can see them as bijections, right? So this is a bijection, and then you just change the order of your intervals. So it's going to be like this. Like this. I mean, the length should be preserved. It's not on my picture. I know that, but it's not that. I hope you can forgive me. So this is an interval exchange transformation. It is encoded by. If I assume that this is an interval 0, 1, then it's encoded by two parameters. So first parameters is how I divide my interval into subintervals, and the second parameters will tell you how do I interchange. How do I change the intervals? So each IT is encoded by pi lambda, where pi is a permutation permutation of the elements. I will denote the permutations of the elements by S0D. So actually just the elements is SD. Why do I need 0? Well, because I want to exclude a very nasty situation. For example, if I had a situation like that I have two intervals which they go just like that, then I can just divide my intervals into two intervals and just consider the dynamics on two of those intervals separately. It's not interesting. So the 0 means that there is no initial interval that is composed of the intervals of the partition, which is sent into itself. Okay, and lambda is a parameter from the space lambda d, right? Where lambda d is where lambda d is the set of vector, let's say w, a set of vectors w, right? Which w I from I equal 1 to d, such that the sum of all of them is 1. Because they have to give a local interval.
I have a question about S0D. Is the situation when union of some disjoint intervals permute allowed? So, for instance, if you permute first and third between each other, and second and fourth, for instance.
Maybe when they're equal lengths. You mean that you could still get an invariant subset, but not necessarily at the beginning.
Yes.
Can I try to draw what you said? So we said we have three intervals, and then the first goes to here, this third goes here, and second goes between them.
No,
somewhere else.
Can we go to fourth, for instance?
And they are of equal length. This is
then you can
First
extend.
For instance,
But
yes.
this is absolutely acceptable, because if you just perturb this situation a little bit, you will lose this property. So it's some bad or good, depending what you're looking for. It's some point which in this space of parameters, which is special. It's monergodic, because then you will get you just get those intervals are like interchanging each other, so you get a very natural invariant set. But it's valid. It's a parameter that needs to be considered in the space. We don't exclude it. It's just that typically it's not considered. Why? Because we have the results by Mazur-Beach. They say that for almost every with respect to Lebesgue measure in this space, the interval exchange transformation, if the permutation is with the 0, then this is actually uniquely ergodic, and even we have new result 15 years old. Result by Avila and Forni, where they proved that actually for almost every parameter you have even weak mixing. So this is a very rare situation.
Historically, I think minimality was assumed.
I mean minimality. So minimality it's actually also a very good example, because minimality can be obtained already if you assume that all those numbers here are rationally independent.
Because you need something like irrationality of rotation number for the sample, and corresponding condition is minimality here, I think.
It's not equivalent.
No, I don't say equivalent. I say historical, I think.
Historically it was, so it was even it's very surprising that if you just assume rational independence, it doesn't imply ergodicity in this world, for example. So there are rationally independent parameters. Examples constructed by Michael Keane, where he showed that you don't have ergodicity with respect to Lebesgue measure, because you have ergodicity with respect to some other measure, but with respect to Lebesgue measure, you don't have. So yes, but we do consider this parameter. And I already said that loud, but I hope it's fine with you that if I say almost every in this space, I mean Lebesgue measure on this simplex, This is very important because in a moment this would correspond to almost every rotation type, or almost every rotation number. So now we will construct something called combinatorial rotation number, which is exactly the rotation number of which is typically considered for GIETs. So how do we find, how can we see if I have a rotation, right, I have a rotation, so for example, rotations with this would be, say, 1 minus alpha, right, and I have a rotation, I didn't say that the rotation is just an interval exchange of two intervals. So how can I find A1, for example, the first partial quotient? So what I can do is I can cut my domain over here. So I see where is the image. The image is here. And then I'm cutting the domain and I'm considering the first return map to this interval. Then, okay, the first return map is just going to be this rescaled, I mean not rescaled, this rotation. So then I do it, so then this interval goes over here. I do it again. And basically how many times I can do it, as long as this interval is shorter than whatever remains here, and the exact amount of time which it takes is A1. But, so this is the concept, so from this picture, I can somehow, if I just don't know what my rotation number, what my rotation is, if I know how much time I do this procedure, so then the roles are changing. So now this guy is going to be longer, and then I'm doing it the same with this other interval, and then I'm recovering A2, A3, A4, and so on. So from this procedure, I can recover the rotation number. So this idea served in the 70s to introduce for interval exchange transformation the process called Rosevich induction, which is the standard renormalization process for the interval exchange transformation. So basically, picture is exactly like that. So we have my interval exchange transformation. I will try to, I'm making it on purpose, the last one to be longer, shorter than the last one. And what I do is I look, so this is before and after. Okay, so this interval is over here, this one over here, and so on. And this is assumed permutation is symmetric. It's not required, but it is in my case. So what I can do is I can consider the first return map exactly like for rotation to the interval, which is the longest of the, which is obtained after cutting the shorter interval either before or after this or after the transformation. In my case, in my picture is the first one, so I'm cutting over it. It's before, so I'm cutting over here, and then I'm considering the first return map to this interval, and okay, this is an easy exercise that you will see that you get again an interval exchange transformation as your first return map, but this time it's going to be new discontinuity point over here because it corresponds to interval which went over here, and then it goes back exactly where this interval was going. And analogously, you can define, so this is so-called type 0 because the loser for the shorter interval was before, and there's also type 1 where the shorter interval was afterwards. But now what is very important, which differentiates interval exchange transformations from rotation, is that permutations has changed. Because right now we started with a symmetric permutation, but it's not a symmetric permutation anymore, right? So we have a new permutation, and so we have a new permutation, and then actually if we if we continue this process, we expect this permutation to be changing all the time. Of course, we don't have infinitely many options because there's only finitely many permutations of the alphabet of the elements, but still we obtain something called rosy graph. So definition.
So you will again always obtain the permutation of D elements?
Almost always. So if you assume very mild conditions, so you want to avoid the situation where the first and last intervals are equal. So then you actually, so you can do two things. You can either say that the algorithm stops, which is most of the people do, but if you for some reason want to continue, you can in general continue, but in some sense the number of intervals will decrease. It will never increase, but it can decrease in this situation if you allow even. But usually people, since for that you would for this to not so for this to happen, you would have to be able to solve some linear equation in the lengths of intervals, and you have countably many of such linear equations because you have like it's always you get some finite linear combination of points, integer final combinations of the lengths of intervals. So in general, you are excluding a measure zero subset in this space. But if you really want it, you can do it. Okay, so now I will say so definition. A rosy class is a minimal invariant subset of S0D under the renormalization. The renormalization, I mean this process exactly. I didn't give it a name, sorry for that. So maybe here I will write the first return map to the interval obtained by cutting the shorter of the last intervals is called rosy. It's called okay. It's not the first. This procedure is called. But let me not write this again. So it's called Rosevich induction. Sorry. Of course, it's not the first. So this is the image. But let me just state it this in incorrect way. I hope you forgive me. So we have this Rosevich induction, and this gives the renormalization R. And finally,
and this depends on lambda. So for different lambdas, a priori at least you get different classes.
Even for for lambdas, no. For lambda, so the rosy graph depends only on the permutation. It depends only on the permutation. So it's so if you have so this is a subset of the space of permutation. I mean, it's not that easy to see.
No, I don't understand, because for rotation you have the same permutation.
It's always the same permutation, but in rotation you simply don't have another choice. And it's also true.
And, completely different things may happen if you renormalize with different starting lengths.
Yes, but the question is, so it's a minimal thing. So because maybe I stated it wrong, but here I mean it's minimal invariant subset of S0D, but this subset does not depend on lambda. We don't want it to depend on lambda.
Okay.
So so because it's not only about, so what depends on lambda is a single step. So in a single step, you go from pi to some other permutation, say pi 1. And you are right. If I take a now different lambda, so for example, I reverse the type. So now the shorter will be after transformation, and the longer will be before transformation. Then I will get a different permutation. So right. So actually, okay, I can try to maybe draw the picture, which will give us the. I will try to make it symmetric somehow. Okay, so it's going to be like that. It's going to be okay. 1, 2. And now I'm going to cut over here, right? And now I actually get that this interval goes over here, which goes over here, and I get this is a different permutation, because here I got that the first interval went to the last one, and here the first one to the second one. So in this case, the permutation that we get depends on lambda. You can actually choose that these are the only, you can prove that these are the only options. So because basically what type of permutations you are going to get depends only what is the relation between the first and last interval before and after intervalation transformation. But these are the only two options. But now, so the rosy class is a subset which is invariant under this procedure. So in the rosy class, you now have to be able to start from this new permutation. So you somehow start with your permutation, and now you want to deduce what is the rosy class. So you first do the rosy transformation, this rosy beach induction, and you get two new permutations. So you add them to your class. But then you start with those two permutations. You do exactly the same procedure. You get two permutations. Maybe one is going to be, some of them you already could have, but nevertheless, you add all those permutations to your class, and so on and so on. So when I mean minimal subset of SD under the invariant invariant under renormalization, I mean also including all the possible iterations, all the iterations of R. Wherever they are well defined, of course at some point they may be, for some lambdas, they may not be defined, but for example, if you take lambdas such that they are rationally independent, then you are actually, this is not a very difficult proof, but you can prove, but also not very trivial, that this process is defined indefinitely, so you can do it infinitely often, basically. This process, you get new permutation, new intervalation transformations, and so on and so on. So in general, this SD, maybe I should give a name, rosy class G, is, so this G is, so of course it has to be finite, because this is finite, but in general, it contains more permutations than just 2 or 3. If you increase the number of intervals, it also grows for quite a lot. And we don't actually know full nature of those subsets even yet. For example, if it contains always a cyclic permutation, this is an open question still. Okay.
So to clarify, the normalization is a multi-values function on the set of permutations, right? Depends on the.
So the renormalization.
Two values.
If you just consider it on a set of permutation, then yes. Then it's like two values. So to each permutation you assign two values. Those values will depend on the lambda. It's defined like very precisely, but if you have lambdas. If you don't have lambdas, you don't get this. So
also, A minimal means that there can be many rosy classes.
Yes.
Okay.
So in general, yes, but you will not find an example in the lower than 5. So you have to go a little bit, or maybe, I think, okay, sorry, I misspoke. 4 is enough. So, okay, but I can write an example, but I will not prove it right now. So if you, for example, for 4 intervals, you will take the intervals, the symmetric permutation and the permutation of rotation type, which means that we get something like that, then they are not in the same rosy graph. You will never obtain from this one, and from this one, this one. Okay? For whatever the permutations are. I could explain, but maybe I want to, move a little bit forward. So, finally, I can tell you what does it mean to be of bounded type. But thank you, all those comments were very useful because this 2 to 1 is going to appear now. So let's go back a little bit to the rotation. So in the rotation case, I've got one permutation which I just draw symbolically of 2 intervals, but since I've got colors, I will use them. You remember I could have 2 cases, so I could have either longer interval before or after transformations. And both of those processes I'm going to denote with different arrows. So let's say that the green arrow means that we have this, say, top. Top is shorter. And the red arrow will mean bottom. It's shorter. And basically, after all this discussion that I did, what does it mean for the rotation to be of bounded type? It means that you do not, there is some k such that if you do green arrow all the time, you cannot do it more than k times in a row. This is exactly what it means this is basically one-to-one translation of being bounded type. So there exists a case such that both green and the red arrow are not done more than k times in a row. Okay? And for the interval exchange transformation, I've got my...
Wait a second. So this means for the rotation number that this alpha is at most k.
The A1s, A2.
Yeah.
So the if you...
So the digits in the continued fraction expansion are bounded precisely by k.
Yes, exactly.
Yeah. Okay.
Okay. So because basically the number of arrows which you do in a row of one type gives you back A1, A2, and so on. And this is exactly, so this is called combinatorial rotation type, although it's the same for, like I said, it's the same for the rotation, but it's combinatorial because, you know, we have permutations. So in this case we have one permutation, but so what? In case we have more permutations, so we have a graph, so we have we have pi 0, pi 1, pi 2, pi 3, and so on. And okay, so I think I already convinced you, hopefully, that from each permutation you will get 2, again, depending on the type you do, you have 2 arrows, but you don't have to get the same permutation.
Also, can you get back this same permutation?
Yes.
So it's possible that one of the arrows goes back to the permutation?
Yes, it is possible. For example, if you do, sorry, on the top of my head, I have a very simple example.
If you have rotation.
If you have not only rotation, but if you have rotation type. So if you have exactly a permutation which goes like that, then this is going to. But there are more intricate examples as well. Not so many of them, but still. So you have this, and then you have again like some arrows. Let's say that this one goes over here. Say this one goes over here, and then we have something else. Moreover, you can actually prove, but this I'm not going to do, that you have not only 2 outcoming, but also 2 incoming arrows. So you can also find exactly two permutations that go inside each So it can be proven. And now the bounded rotation, finally I can say what does it mean. So bounded rotation type for interval exchange transformation means that there is a, for every arrow in this graph, there is a, I started wrong, there is a uniform bound K on the number of iteration of the renormalization process. We have to wait to see the same arrow 2 times. Okay, so if I see one arrow, then in not more than K iterations of the renormalization process, I will see the arrow again. This precise arrow. I'm not talking just about type. I'm really talking about the arrows here. So it's not only about the color, but it's really about this precise. And this is what is called combinatorial rotation number. It corresponds to so if you take an interval exchange transformation, you will get its combinatorial rotation number. Moreover, you can prove that on a full measure set over here in lambdas, and for every permutation, you will get that this combinatorial rotation number is given uniquely. It's actually, if you, for example, take, this is more or less how you prove unique ergodicity, that you get some nice, I mean, it's a tool that you use to prove unique ergodicity, but this is just a comment, not important. So whenever I say a bounded type generalized interval exchange transformation, what I mean by bounded type, I didn't say yet what does it mean for, but for bounded type interval exchange transformation, I mean exactly that there is a bounded amount of time we have to wait to see every arrow twice. So now, so now I'm finally over with the IETs. So now I can say, what does it mean for GIETs? It means exactly the same thing. So for this process that I did over here, I don't have to do it just for interval exchange transformation. This, I simply, if I have a generalized interval exchange transformation, let me draw a picture. Let me draw a crazy picture.
It's just the distance exchange, not the permutation.
So we have this. We have so for example, this interval, but it now will become longer because, for example, I am expanding on this interval. Now this interval will become shorter because here I contract it. Here I will get more or less the same, and here I get contraction again. So, and this is not affine. So this can be affine, but doesn't have to be. So I just drew the pre-image and image of the intervals exchanged by the generalized by interval exchange transformation. And now I do exactly the same thing. So I do not care about anything but the lengths of the last intervals before and after permutation, and then everything stays the same. So when I'm saying generalized interval exchange transformation with a bounded type, I mean that each arrow is done with a limited amount of time, and then this actually tells you what is the so now I think explained all the notions that are here, but now, okay, why is it a natural thing to, so in general this theorem is important, but actually it was done by Yokos, and this should be set over here, that now for a typical IET, typical I mean full measure set over here, if you consider this IET, you can consider it as a rotation number in this sense. So you just encode which paths you are taking in which order, right? So this rotation type is going to be exact. You can think of it as a sequence of paths in this graph. Then a generalized interval exchange transformation, which has exactly the same rotation, this combinatorial rotation type, is semi-conjugated to this interval exchange transformation. Okay, so let me let me write this down. So this is theorem by Yokos. For a typical IT T, a GIT F, a GIT F with the same.
This typical is with respect to lambda?
With respect to lambda, Lebesgue measure in this set, with the same rotation number, this combinatorial rotation number, ST, is semi-conjugated to T via, this is important because we are talking about not continuous maps, but it's actually via non-decreasing continuous map, H. Okay, so this shows this proves that this is the correct language to consider. So if we have somehow, if you do a lot of renormalization, which I am not, but for example, if you do a lot of renormalization, it is natural that the maps that should be conjugated should, if you chose your renormalization process properly, they should behave more or less in the same way. And this was formulated by your course. Okay, so now I guess finally I have to state what we proved, since I have 10 more minutes. And this is what is all known. Nothing more is known until now. So there are now two things that we can consider. So first of all, we can lose the bounded type. And then we can actually, since this is just a rotation type, remember this is the circle break equivalent. What we are actually losing is we do extend our results to higher number of intervals. Okay? Sorry, for higher number of intervals and non-trivial permutation. Non-trivial permutation is also important. Okay? Okay, so we have theorem A. Theorem A, so for almost every IT T equal pi lambda. So again, in those parameters which I just erased. So pi is the permutation, lambda is a length vector from the positive simplex of lengths. For any, here I will write this, but I will not define this. I will more or less just say what it means. Boundary equivalent. GIT F and G of the same rotation number in this sense. S T. Sorry, because we have for almost every IT, and this for almost every IT with F and G. Actually, I should write it before, but okay. With I being of rotation type or be a permutation of 4 or 5 intervals. Okay, for almost every assume C3 here. F and G, which are C3. I'm rushing too much. Which are C3. So we lose some regularity. So we get C1 conjugated with the assumptions that they are C3. So they have the same rotation number, so we expect them to be conjugated via your cost, but we can actually say a little bit more about the regularity of this conjugacy. And okay, and now I need to tell you what is boundary equivalent. Okay, I will not tell you maybe very formally, but you can actually imagine what it has to be. So in the case of the circle diffeos, we needed to know that the breakpoints are sent into breakpoints, and the ratios of the derivatives had to be preserved if we even can have a hope for C1 conjugacy. This is exactly the same condition in this case. So first of all, the discontinuities now of the GIETs have to be sent into discontinuities of the GIETs, and proper derivatives have to be preserved. It's a technical condition, but it's really just a generalization of this condition being break equivalent. So breaks sent into breaks and the jump ratios being preserved. Okay, they are C1 conjugate, and we have a theorem B, which is a little bit of a corollary from this theorem A, but still you have to do something. So for almost every t pi lambda, but just of rotation type, any two, this is direct generalization of this theorem. Any two f and g with a circle homeos, circles, okay, so circle C3 diffeos, F and G, with D breaks, which are break equivalent. Once again, it means that breaks are sent into breaks by what we know exists on continuous conjugacy, and the proper ratios are preserved. They are are C1 conjugate, but as circle diffeos. So where this difference comes from, because there is a subtool. Here we are considering maps of the interval, and here we are considering maps of the circle. The topology is slightly different, right? If you consider it on the interval and when you consider it on the circle. So basically we say, in particular, what I'm saying is that if we have a circle diffeo, and when we just want to apply theorem A, so this is my circle diffeo, if I wanted just to apply theorem A to this situation, because this is what we do in the end, we use this. But then, if you see it in the world of the generalized interval exchange transformation, then this world sees this point as a discontinuity point, even if it's really not on the circle. Okay, so this is where this difference comes from. So in some sense, this C1 conjugacy would appear to be break, so it would not have to send properly this point into so you would get, even though you started with two things which were smooth, sorry, not smooth, but which had jump ratios being 1 at this point, the conjugacy itself would not have to be preserved, would not have to preserve that. But we actually proved that by doing some small parameters trick, you can prove that. And let me just see that, maybe I have 3 minutes, so let me just say about the strategy very quickly. I think I already, I think it was important to introduce all those notions. So the strategy is relatively simple if you know a lot. So, but we were happy because we know a lot. There is a result first started by Yokos and then improved by Selim, Gazouani and Corina Uchigai, when they proved that actually if under those assumptions, because those assumptions come in from nowhere a little bit, right? Y4 or 5 or rotation type. I didn't say why this is required, but actually, because in those cases they were able to prove that if you have a minimal, if you have a nice generalized interval exchange transformations, which is minimal, actually we also assume minimality, which I didn't say, sorry, minimal. We can deduce this minimality, but let's just say it's minimal. So if you have this, then you have something called affine shadow. So you cannot renormalize the same way as, so if you do this renormalization, you will not be approaching the interval exchange transformation, because for interval exchange transformation, all the derivatives is 1 everywhere. So there is no ratios to consider, there's nothing. But what you can do if you have different ratios in the discontinuity points of the left-hand side and right-hand side derivative, what does have this property is actually this thing, the affine ITs. So the transformation of a circle or interval, okay, let's say interval, which looks more or less like this. So you have like this, and this. So it's a piecewise affine map. And there you can produce those ratios of derivatives that you want to do. And actually you can do the renormalization process. And this is very difficult, but people were able to prove that if you start now renormalizing, so you see like the renormalization, you get again the map of the interval, and then you extend it, like really renormalization, so you extend the domain to be of length 1, then your transformation actually starts to, under those assumptions, it starts to look more and more like affine interval exchange transformations. And actually what we prove is that this procedure will give you a candidate to be actually, so you will never be C1 conjugated to an IT, but you will be C1 conjugated to this affine interval exchange transformation. And then we prove that both of those guys, which have the same rotation number, are actually affine C1 conjugated to the same affine guy, and then we just compose the conjugacies and we get the result that we want. But there is still a lot behind it. But I hope that at least I introduced properly the subject that we're working on, and thank you for your attention.
Yes.
So I have a question because I might have skipped this. So in theorem B, you are assuming that D bounds. Is this for any D?
With D breaks.
It's for D breaks, yeah, sorry.
Any, like, you mean any big D, yes.
Yeah, like
any
17.
Yeah, yes.
Okay.
I mean, I didn't write this down, but we assume that 0 is one of them, or 1 is one of them, because you can always just rotate your, but this is, but yes, in general we have any number.
So you don't assume it's like 4 or 5, so.
No, the number, so in this case it can be 1,000, million, I mean any amount you want, in the rotation case. The rotation case is somehow more understood.
Yeah.
There more results, so we had more tools.
It's still very important.
In which sense theorem-based generalization, in the sense that you prove also C1 in this point on the boundary?
We have, this is, the difference is here.
Almost every, I see, okay.
This is the main difference. So here they prove just bound, sorry, I didn't say very important thing. So bounded type is a measure 0 in all parameters that you can imagine. So now we have almost every. So this is the biggest difference. I mean, we assumed slightly more. So the proof is that we assumed something more on the regularity over here. But but okay. So it's a generalization if you put 3. But the proof is yes. So, but yeah, the most important part was to prove it for almost every, and there's actually a lot of studying of this this normalization procedure comes into play.
Is there some generalization of Diophantine condition for the rotation, combinatorial rotation types?
It's an excellent question, but so it's not. It's yes, but it's rather written in the language what we want than rather what we can deduce from the parameters. So we basically we write that we want, for example, that we need to know something about the lengths. So we, for example, we know that we want to know that the lengths do not of any of the intervals which are exchanged do not shrink too fast to 0. So this is one of the. So this is in some sense a proper Diophantine conditions give you that for rotations, and we have equivalent of that. But if for example you would like me to give you a specific description of the initial parameters, then this I cannot do. So every of those conditions is in the language exactly of the already combinatorially involved language.
Are there any other questions? If not, let's. Yes, please.
Okay, the short one. So you said that the problem is when the segment shrinks too fast.
For example, yes.
Can I just curious that in fact the normalization segment inside the initial segment it just does not shrink to 0.
This never happens.
Okay.
This never. It's about proportions, not about the domain. If it's okay, it's not. At least for IETs, it's already for IETs. It's not that easy. It's a little bit technical to prove, but it's classical already. That if you can renormalize, then you will always shrink to 0. The whole domain shrinks to 0. So basically you cannot because to not be able to shrink to 0 would mean more or less that some of the intervals are never getting shortened by the process. But this would lead to a contradiction with the fact that our perturbation does not fix any initial interval. This is how the proof more or less goes. Okay.
Okay, now we can thank Przemysław.
Thank you. Goodbye. Thank you.
Thank you. Thank you so much.
Yeah, thank you. Goodbye.
Thank you. Thank you. Goodbye.